It's a pleasure to be here. I'm very grateful to the organizers for all the work of making this conference go. And it's my first time in India, so I'm keeping my eyes open. It's fun. Okay, so I want to talk about joint work with James Farre and Landesberg. And the subject is kind of in between dynamics and geometry. So I want to talk about Horocycle flows. So the Horocycle flows will be on a certain family of infinite volume hyperbolic manifolds. In particular, it will be on Z covers of compact hyperbolic manifolds. Is this too small? I just realized. Yes. Okay. All right. So Horocycle flow. You'll see these words again. Of closed hyperbolic manifolds. And in fact, most of the talk will be in the setting of surfaces. So maybe I'll and the goal is to understand the structure of these flows and to relate it to hyperbolic geometry, because all I really know how to do is hyperbolic geometry. So let me talk for a minute about the history of this subject. I don't know if it's a broad audience, as the other speakers have said. All right, so here's the general setup in dimension 2. So suppose that sigma is a hyperbolic surface, so it's the hyperbolic plane modulo some discrete group, and I can and the hyperbolic. So and then T1 sigma is a quotient of so T1 is the unit tangent bundle of sigma, which is a quotient of the unit tangent bundle of the plane. This is a 3-dimensional manifold that fibers over sigma. And the geometric way to think about this is, the group theoretic way to think about this is that T1 H2 can be identified with G, which is just the isometry group PSL2R. Just because, if you have, here's a picture of the hyperbolic plane, and you fix a certain base vector, a single vector that acts as a base point for any other vector, unit vector in the plane, there's a unique isometry that takes this one to that one. And so the set of all unit vectors is identified with the group in the usual way. And this space, and therefore the quotient space, has a nice geometrically defined flow. In fact, 2 flows I want to talk about. So first of all, the geodesic flow. I'll write, let's see. So this is going to be some family of maps AT, which act on the unit tangent bundle of the surface. And also, of course, they act here. And they're just, the picture definition is you start, if you have a point in your space of tangent vectors, then AT will take that point, it will flow forward along the geodesic determined by this arrow to a new tangent vector so that the distance is exactly t. Okay, the signed distance. So this makes sense for t, a real number. That's the geodesic flow. And the Horocycle flow, I'm gonna write it as nt, also from T1 sigma to T1 sigma. And there's actually 2 choices here. I want the stable Horocycle flow. So that means, so this point, it doesn't just determine a geodesic, it also determines a horocycle, which is orthogonal to this geodesic. And I can slide right and left along the horocycle. So that's what nt does. It slides me a signed distance t along the horocycle. Okay, and you can write these, if you want to have the group theoretic version, you can write these as matrices. They're subgroups. So you let A and G be the subgroup well, in fact, they're called AT, and they're in fact the matrices e to the t over 2, e to the minus t over 2. So this is the diagonal subgroup that acts this way, like the geodesic flow. And then there's what I'll call N in G is, and I think to do this correctly, I should put the T on this corner. So it's this parabolic subgroup. And the relevant relation, I want to make sure I get this right. I'm saying, by the way, if I would like to say that I have now, a little bit of experience thinking about this flow, like at least a couple of weeks, and I think there's a 60% chance that I have this right, which I feel is good. 60% is better than 10%. So it's better than coin flip, I guess is my point. So I mean, because the t can go here or here. So what do I actually want? I'm going to write this carefully. Where was it? I want this relation to hold between them. AT n s a minus t is equal to n e to the minus ts. So what that means geometrically in this picture is the following. It says, if you interpret this correctly, so I should say the way that I interpret this action is by the matrices acting on the left on G. You have to set this up correctly. I think it may be more common to have them acting on the right, but my co-authors and I, after going back and forth, decided we liked having these act on the left. So that's how we're going to write it. And that's, I think, the correct choice for that definition. So what's going on is this. If I start somewhere, so the horocycle looks like this, right? It meets infinity at the forward endpoint of the geodesic ray. And so if you look at NS, that takes this vector to this vector. And then on the other hand, if you flow both of them forward by t, I get the t in the right place? Yeah. Then the content of this equation is that the horocycle that you get between these 2 points is exponentially smaller than NS. Okay, so so the geodesic flow contracts the horocycles exponentially fast. That's the meaning of the word stable. If I chose horocycles going the other way, they would be unstable. Okay, so that's the horocycle flow and the geodesic flow. And what is kind of classically known about these? So first of all, one can ask, what are orbit closures? That is to say, you take a point x in T1 of sigma, you apply the horocycle flow to it, look at the whole horocycle, and you take the closure of that inside T1 sigma, and you can ask, what is it? Okay, those are orbit closures. And then in parentheses, I'll also ask, what are invariant measures? And this talk will not be about invariant measures, so I will not, let me not talk about that. In fact, the invariant measures story for our example is actually not so interesting, turns out, or at least not much structure. But this turns out to be quite interesting. So, and also you can ask about the geodesic flow in the same way. So for the geodesic flow, there are many, many different orbit closures. And that's because the geodesic flow on this, even if sigma is, let's say for a minute that sigma is a closed surface, you have this compact space with this geodesic flow on it. The geodesic flow is an Anosov flow. It has expanding and contracting directions. It produces a hyperbolic dynamical system. So it has many, many, many periodic orbits and many things which are invariant, which are closures, but are not the full thing. There's a very rich structure of orbit closures and of invariant measures. So it's very wild or flexible. And on the other hand, for the horocycle flow, the opposite is true. So this maybe starts off with a theorem of Headland in 1936, which says that if sigma is closed, then nx bar is always equal to the full thing. So in other words, all orbits of the horocycle flow are dense. And I should say if the volume of sigma if it's not closed, but the volume of sigma is finite, then nx is either everything, or nx bar is either everything, or nx is already closed, and it's a closed horocycle associated to a cusp. So you should have this picture in mind. Here's a hyperbolic surface with finite area. And if this cusp has a kind of family of horocycles associated to it. Each of these horocycles, if you look at the orthogonal vector to it, that's an orbit of the horocycle flow, a closed orbit. They don't have to be embedded in this way on the surface, because if you push them further and further out, they start to become quite complicated. So there's kind of, if you push this out, it starts to interact with the topology of the surface. So it can be a very long closed orbit, but they're all kind of concentric with this cusp. And that's all that can happen for orbit closures. I think there's similar statements about invariant measures, which are due to, I think, not to Hedlund, actually probably to people in this room, I think to, to Furstenberg. And there's a paper, I think, by Donnie and Smiley about invariant measures. So I'm actually not so familiar with the literature on this. Is that a fair attribution to the invariant measures question? So, okay, so this is the end of the story in the sense of what this question is for these finite area surfaces. And I want to say, without really explaining, that this is kind of the first step in a vast and deep subject, in which this is not just for other dimension of hyperbolic manifolds, but for basically any homogeneous space. And there's this, so this is maybe relevant for this conference, right? So Raghunathan, Argulis and Ratner, Dani. And so on, right? So there's a long list, which I shouldn't try to replicate, that extends this kind of rigidity of horocyclic actions to a much broader theory. Okay, so that's a very large subject that that is not the subject of this talk. So what do I want to talk about? I want to talk about infinite area surfaces or infinite area manifolds. So what if the volume of sigma is infinite? Well, there's another dichotomy, which I want to just mention very briefly. You can talk about geometrically infinite finite case. Well, so in 2 dimensions, geometrically finite is synonymous with finitely generated. So, so for us, this really means finitely generated. And then there's essentially the same picture, except, so it looks kind of like this. So the surface, here's an example of an infinite area geometrically finite surface. It has infinite area out here in this end, and then there's some finite part over here. If in the universal cover, what you see is, without getting into details, there's a limit set which is some closed invariant set for the group, which is not the whole circle. And then there's these complementary intervals to the limit set. And those correspond to kind of a universal cover at infinity for this end. And if you have in the surface a vector that points out to infinity, so it lands in one of these complementary intervals, then somehow the dynamics aren't interesting. Then basically this horocycle around there also goes out the end eventually. And so so the horocycle makes a closed orbit. So in order to get anything else that's interesting, you should really be looking at points, at vectors that point into the limit set. Here that would look like this. You have a vector, and it somehow essentially means that it stays in the convex core for its whole life after some point. And that's also not what I want to talk about. So in the geometrically finite case, there's a kind of similar picture, except you have to kind of make this distinction. Are the vectors escaping, or are they kind of sitting in this compact part? And right, so okay, so I want to talk about the geometrically infinite case, and now we have, I think it becomes a sort of zoo where lots of things can happen, and there's not much coherent understanding of what the possibilities are. But we got interested in a particular geometrically finite family of examples where there's just enough structure for something interesting to happen. And that's the case I want to talk about. So I want to think, so now here's what we're actually going to talk about. So let's let sigma 0 be a closed hyperbolic surface. And let sigma be a Z cover, which means, of sigma 0, that just means that sigma admits an infinite cyclic action by isometries whose quotient is sigma naught. So it kind of looks like this. Here's a picture of sigma. Kind of some periodic picture here. It's a hyperbolic surface. Maybe I'll draw these. Okay, so that goes off like this. There's a isometry. There's a Z action like this, and the quotient is in this example. The quotient will be a genus 3 surface, right, where this circle goes to this circle, and these two holes are these two holes. Okay, so that's the setting. So that's a geometrically infinite group. It's infinite generated up here, and I want to understand Horocycle orbit closures here. That's the goal. Are there any questions? Okay. All right. So what is it that I want to say about this? So the good news is that we actually kind of know what's going on in this case. Actually, let me tell you what the theorem is roughly already. I'll kind of advertise the theorem before I start really talking about it, and then, or at least a part of the theorem. So here's one theorem that can be said about this. So this is with James and or me. So orbit closures. So n orbit closures in sigma, in T1 sigma, if it's a Z cover of this type, are either actually, let's number them like this: 1, 2, and 3. So they're either three-dimensional, so they're everything. So yeah. Or they're or the Hausdorff dimension is 2. So here the Hausdorff dimension is 3. It's a 3 manifold. Or the Hausdorff dimension of an orbit closure is 2, or the Hausdorff dimension of an orbit closure is 1. And I will tell you a little bit about when these things occur. In both these cases, even though the Hausdorff dimension is integer, the sets themselves are quite intricate. They have a fractal structure, but not quite enough of one to produce non-integer dimension. Okay, so it's quite different, for example, from the geodesic flow, which has all possible Hausdorff dimensions for its orbit closures. And it's also different from the closed case where you only get case 3. So, all right, so I'll try to that's the goal, is to kind of try to explain something of what goes into this theorem. Okay, so, all right, so I promised that I would talk about geometry. I guess this looks like geometry, but really this is just dynamics. But I want to relate it to a kind of, well, specifically, I want to relate the geometry of this Horocycle question to the geometry of geodesics in the surface. And that comes from a theorem of Eberlein. So I think, so this is Eberlein in 77, and then Dalbo. I'm a little confused about which parts of it were done by who, but I will, and Makuran Shapiro. Yeah, it's more recent, I think, in 19. So there are different generalizations of this, but I'm just going to talk about the case, about our case. And the theorem says the following. It says, well, let me write it. It says, so X here is in T1 of sigma, and all I need here, it's kind of true in general, but I'm going to use it in our setting. Then Nx bar is non-maximal if and only if X is quasi-minimizing. So I have to explain what this means. Okay. So what do I mean by non-maximal? Non-maximal for us, in our example, just means not dense. So it means Nx bar is strictly contained in T1 sigma. Why am I being cagey about this? Because it's a slightly different definition in the case of these infinite area things where the limit set is not the whole circle. In our case, the limit set will be the whole circle. There aren't any ends like this. And so that turns out to be the right. So this really just means, non-maximal just means that the Nx is not dense. And what is this quasi-minimizing? So this is the interesting property. X is quasi-minimizing if the following estimate applies, if there exists a constant such that if you look at the geodesic flow time t starting at x and ask how far is it in the manifold from the beginning. So how far can this be? It can be no bigger than t, because these are connected by a geodesic of length t. So the distance is no bigger than t. How much smaller can it be? The estimate is that it's at least t minus c. So the image you should now have in your head is that I have my manifold, whatever it is, and I have x is quasi-minimizing if when I flow out in this direction, I get out as efficiently as possible, which means that my error is at most c, some constant. Okay, so that's so that's the theorem, and that gets us to thinking about such rays. I'm not going to talk about the proof of this theorem, but a lot of the ideas that go into the proof will end up as tools that I'll try to talk about before the talk is over. Okay, so you'll have, I think, by the end of the talk, if I succeed at all, you'll have some intuition for why these two things should be related, even though the theorem itself is a little bit more involved. Is the definition clear? I want to emphasize there's no multiplier here. Okay, it's not just linear escape, it's linear escape at rate 1 with a constant error. Okay.
Does that really mean that after some finite time,
this is an excellent question. So it means that in some limiting sense, you get closer and closer to actually being minimizing. So, right. The limit can occur. So you're going out to infinity. So limit in the surface doesn't occur. In our setting, the whole point is going to be that it's in this picture. If you take a, so I'll say this in a second. If you take a quasi-minimizing path that goes at one of the ends, and then you push it into the compact surface, you're getting a geodesic of some kind that's running around in this surface. And you can take limits of that. You can take limits up here and then lift them back up to here. This whole thing is periodic, so you can lift it in many ways. So you should think of that. You should think of you're running off to infinity and you move your base point along with you. And you can ask, what is the limiting picture? And that is in fact exactly what we study. And the limiting picture is an interesting object. Okay, but yeah, so I'll get there in a minute. So first of all, yeah, no. So let Q be script Q be the set of all quasi-minimizing points. The constant C depends on the point. It can be any constant depending on the point. So here I don't fix the constant. So then note that the Q is A invariant. That's pretty clear, because if you just move your base point, you have this ray, and you move your base point either forward or backward, and then do this arithmetic, you will see all you've done is change the constant C by at most the amount you moved, or something like that. So it's clearly invariant under geodesic flow, but it's also N invariant. And that's because if you apply N to this thing, so you don't quite know what it's doing, you could but let's draw a small amount. So here's a little N, a piece of the N orbit of X, and look at this point on the N orbit. It, by definition of N, this thing is asymptotic to the original ray. And so this estimate is going to hold for this other point also, again, with a different constant. So you can, and the interesting part, if you can go really super far, right? Like you can go 100 years along the Horocycle, and it'll go, you don't really know where, but you know that once you get there, if you start flowing forward, you will eventually be asymptotic to the original ray. So it is, so this property is N invariant. So K is sort of foliated by, you know, it's like AN orbits cross some kind of set. And this set is essentially a set of points at infinity, right? Two rays are the same under A and N exactly when they have the same endpoint at infinity. So it's these endpoints at infinity that we'd like to understand as part of the story. Okay, is that clear? Okay, so, and how am I doing on time? Okay. All right, so now the next, okay, so that's kind of the starting point, is to think about this property of quasi-minimizing and try to understand what are the quasi-minimizing rays in this hyperbolic manifold we care about. I'll leave it as an exercise that in any non-compact manifold there exist quasi-minimizing rays. It's kind of just not hard to find them, but you can't say much more than that in general. But in these examples, we'll be able to say a lot. Okay, so what is Katie's observation? It's that if you start with X in Q, then if you look at ATX is still in Q, but it's going to be when T is positive, ATX is quasi-minimizing with constant going to 0 as T goes to infinity. It gets better and better, more efficient. And why is that true? What is this saying? It's saying that the length of the curve which is T, can overshoot the distance, but only by a constant, which means I only have that much to waste as I go off to infinity. If I drive along and I'm wasteful once, and then I'm wasteful again, the waste adds up. And if in the first 100 million years, the waste is still roughly 1, and then I wait another million years and it's again 1, then these ones will add up, and the original ray can't have bounded waste. So anyway, it's really an exercise in the triangle inequality, but you can check that this is true. So if you could take a limit, the limit would be quasi-minimizing with constant 0. And that's exactly what happens. So what you can do is you can take so you could take a limit, right? So let's let Q omega be the lift of the omega limit set of Q projected downstairs. So it's the picture I drew before. You start with a quasi-minimizing ray upstairs, you push it into the closed surface, you follow it in forward time and look at where it accumulates. Okay, and then you can pull them back up. And what you immediately get is that Q omega is a union of geodesics, of geodesic lines that are exactly minimizing. So that is to say, for the limiting lines, you get things like this. You get the distance for any point on one of these lines. The distance, is exactly t. So there's somehow, in some funny sense, they're isometrically embedded in the surface. So there's some picture. Okay, and then the theorem that you can prove about this is that this union of lines maps to a lamination. Actually, there's a tiny technical point. Let me write it without explaining. This maps to a current in sigma 0. What I want to say is it maps to a lamination. What's the difference? What is a current? A current is a closed collection of lines inside a surface, geodesic lines. A lamination is a closed collection of geodesic lines that have no intersections. And I want to say that that's true here. And I have a tiny caveat, which I won't elaborate on. So I want to say it's a current whose chain recurrent part is a lamination. So let me not explain what this is. If you know what it is, it's fine. And if you don't, just pretend that the whole thing is a lamination. You'll get the right idea anyway. Because the difference is very small, it turns out, between, you don't have to get rid of much. So the picture for those who have seen laminations before kind of looks like this. Here's the quotient surface. In the quotient surface, I have an embedded collection of lines. So that means there's a bunch of geodesics that run around this surface and never hit each other. And you might ask yourself, how many such things are there? Well, it turns out there's a very rich theory of laminations on surfaces, geodesic laminations, and there's quite a, anyway, so I'm not going to draw too much more of it, but it's some kind of picture like that, which lifts upstairs to, well, they just lift to some collection of lines, which is complicated and accumulates on itself in complicated ways, but has the property that every one of these lines is isometrically embedded in the surface. Okay, and now you might ask yourself, well, when does that ever happen? What is that? Like, what kind of such pictures can exist? I want to say a little bit about that. I want to have a room for getting back to Horocycle flow, so hopefully we'll have that. Yeah. It's no longer just in the positive direction now, because as I go to infinity, my history becomes infinite after a while, right, in the limit. Yeah, so this is a nice bi-infinite line lamination. So let me take a little side trip to where such laminations come from. So now we're going to take a side trip to stretch maps. So stretch maps, well, Thurston developed the idea of stretch maps as kind of Lipschitz constant optimizing maps between one hyperbolic surface and another hyperbolic surface. This is a slightly easier version of that, which is maps from the hyperbolic surface, a compact hyperbolic surface, to a circle. And I'll write the circle as R mod some multiple. A is taken. I don't know. Some multiple is Z, right? So take a circle of circumference B and map this hyperbolic surface to it. If you have, so what exactly do I want to say? So here's a theorem. And I guess this theorem has a couple of different types of proofs. So I think, let's see. So there's one by Gary Toe and Cassell, and there's another by Daskalopoulos and Uhlenbeck. So this is a more synthetic geometric kind of approach, and this is a more analytic approach. And I think there's also, I think, something by Wolf on this subject, I think. And it says the following: fix a homotopy class phi of maps from sigma 0 to the circle. Okay, then here are two different numbers. There's let L be the infimum of Lipschitz constants. Of maps in this homotopy class. So try to make this map have the least maximum stretch it can. And in fact, the infimum is a minimum. You can always realize it by some map. And then here's a kind of lower bound for L. Let's maybe call it L. I don't have a good name for it. Rho. Okay. Let rho be the supremum of. Let me write it this way: the length. This is over gamma. I think I just want to write simple closed curves. Sorry, over gamma, where gamma are simple closed geodesics in sigma. And you take, for such a curve, you take the length of phi of gamma. Maybe I'll put a star here. So you map it to the circle, and you figure out how long it is. What's the shortest representative in the circle? And then you divide it by the length. So this is in the circle, and then the length in the surface of gamma is the denominator. This ratio is, so it's clear that rho is less than or equal to L. Right? If you can, a Lipschitz map will expand this ratio of lengths, will give a ratio of length most equal to Lipschitz constant. Sorry, this is not the theorem. This is definitions leading to the theorem. Sorry. And the last definition is definition F, a representative of the homotopy class. We'll call it tight or a stretch map, one of those, if rho equals L. Okay, so if this really is the best Lipschitz constant, we call the map tight. So sorry, well, rho equals L is just a property of phi, but rho equals L equals the Lipschitz constant of F. It realizes the Lipschitz constant and also that it's equal to rho. That's what a tight map is. And the theorem is, so sorry, I left the theorem off for the end. The theorem is phi has a tight representative. Okay, and so it has something just like this, and let's say such that the locus where the local Lipschitz constant is equal to the Lipschitz constant, so where the stretch is maximized, is a geodesic lamination. So in our picture here, there's a map of our surface to a circle so that the lines of this lamination, of some lamination, are mapped, well, not asymmetrically, with constant expansion to the circle. I can also note by changing B, I can arrange for L to just be equal to 1. And I sort of want to think about that. So I can always rescale the circle so the Lipschitz constant is 1. And that's the map I want to look at. So these are called tight maps. Well, there might be more than one tight map, but there's a kind of canonical lamination, which is always part of this special maximal stretch lamination. So for every phi, there is a canonical lamination this theorem gives you, so that you can have a tight, so that tight representatives have this phi in their maximal stretch locus, have this lamination in their stretch locus. Is that clear? And I haven't, if I had a longer talk, I would give you an explicit example of such a thing. It's actually an interesting exercise to try to find such examples. It's not entirely clear at first how you would ever, what this actually looks like. And I think I won't have time today to tell you that, but at least accept that as a kind of basic fact. And what we prove, in fact, so our theorem is that, in fact, this chain recurrent part is a lamination. In fact, it is the canonical stretch lamination. For what? So here I had a cover sigma over sigma naught. Here I had a map of sigma naught to the circle, but maps to the circle and covers determine each other, right? If I have a map to the circle like this, I can unwrap the circle and unwrap the surface and get a z cover. And conversely, if I have a z cover, there's a cohomology class here, which gives me the map to the circle. So these two pictures really are about the same thing. That's the point I want to make. This is the thing, that the kind of starting point to our discussion, that these omega limit sets of the quasi-minimizing set are exactly the stretch lamination. And you can sort of see that the stretch lamination has the property we want. If we set this up so that the Lipschitz constant is 1, that exactly says that when you lift, you get a map to R, which is an isometry on these, which is 1 Lipschitz and is an isometry on these leaves, which means that these leaves exactly have the minimizing property we want. So that is what the general picture looks like. And now I want to give you a feeling for how the structure, so the idea now is to show that the structure of this lamination gives you information about Horocycle orbit closures. So what do we know so far? We know that first of all, I guess, yeah. So you have these quasi-minimizing sets, and there's a little more to say, but I want to make just a single point, which is somehow we said somewhere, maybe it's here, that this quasi-minimizing set has these 2-dimensional leaves and somehow parameterized by the endpoints. So what are these endpoints? These are so now the picture is I have a lamination, and in the set of endpoints I get are exactly the set of rays whose omega limit set is in the lamination. So here's a fact about that. Actually, so there's a slightly older theorem of Keenan series, and I think there's which says that the set of so if lambda is a geodesic lamination, in a closed surface sigma, and let's say then maybe we'll call it boundary lambda tilde equals the endpoints of the lift of lambda to the hyperbolic plane. So on the surface, we have this geodesic lamination of some sort, in fact, any geodesic lamination. And in the hyperbolic plane, all these lift to geodesics that all live in the hyperbolic plane. And there's some set of endpoints, which is not the whole circle. It's just whatever the endpoints of all the leaves are. It might be an uncountable set. Typically is an uncountable set, but it's some subset of the circle. The theorem is that the Hausdorff dimension of this set of endpoints is 0. It's a very thin set, even when it's uncountable. Okay, so here's is that statement clear? So this is a kind of very, the fact that in the surface that these geodesics are disjoint from each other forces, it restricts them a great deal. And even though there are many, many such laminations, nevertheless, the set of endpoints is very small. And then there's a kind of, here's a lemma that uses the same idea. So the same ideas that are in this proof give you a lemma. It's not quite a corollary of the statement, but it's a lemma that says that the set of endpoints of rays that accumulate on lambda naught also has dimension 0. That's a much bigger set because there are many ways to accumulate on this lamination. You don't have to exactly follow a single leaf. You can keep going between leaves. So there's kind of uncountably many, there's kind of infinitely many choices you can make as you're accumulating on some lamination. So you get a much bigger set of points, but it still has dimension 0. And as a corollary of this, all orbit closures in Q have dimension less than or equal to 2. Basically because of this picture. Somehow, all the orbit closures have to live in Q. The orbit closures either are everything, which is the case, the dense case, or the whole thing lives in Q. And in Q, everything looks like a surface cross a set of endpoints like this, or at least it's inside a surface. So, so the dimension is no more than 2. And in fact, sometimes less than 2, as we'll see. Okay, so this kind of is the first payoff you get for having this picture. So a priori, the dimension could have been anything between 0 and 3, right? Or sorry, between 1 and 3, and this tells you that it's not. Okay. All right. So now what? Right. So as usual, I don't have as much time as I thought I would, but I want to give some idea now that we have this much set up, I want to give some idea of how we analyze the horocycle orbits using this geometric picture. Okay, that's because so far I haven't done anything like that. I've just talked about the geodesics. Are there any questions about this so far? Yeah. No, this is the set of endpoints of rays whose omega limit set is in lambda naught. Right. So it contains all the endpoints of lambda naught, but it contains more. Okay. Okay, so how do we ever think about an actual orbit closure in a way that's sensible? Yeah, let's see. It's a little bit, okay, here's the basic kind of geometric maneuver, let's call it that. How do you spell maneuver? Uh-oh, I'm in trouble. Okay. I have no idea if that's right. Okay. I usually think of it as a trick, but I think calling things a trick is not a good thing to do in mathematics because we want to think that things are deep and not just a trick, right? So anyway, it's the following idea. So actually, before I describe it, let me make a tiny piece of notation. Suppose x and y are points in the tangent bundle of our surface. I'm interested in the following. I want to know how does the closure of the orbit of x intersect the orbit of y by a. So the picture is this: I have y somewhere, and here it's geodesic, its orbit, and here is somewhere else is x. Okay, and then I follow the orbit, the n orbit of x, and it runs all over the surface, but it sometimes accumulates exactly, sometimes it can accumulate on this line, the flow line for y, the geodesic flow line for y. And I want to talk about that because it's kind of, that's the kind of the part I don't know. That I kind of know that, if I accumulate on some point here, I also will accumulate necessarily on the whole Horocycle through that point. So somehow the picture of the orbit closure of X looks like a bunch of Horocycles all over this picture, some of which are exactly intersecting this line in this way. So I want to study these points, the limiting points. So I'm going to study them by talking about the following object with a weird notation, which I will explain. So z of yx is equal to just the set of all t and r such that a t y is in the Horocycle closure of X. Okay, any such point so it's not on a Horocycle, it's on a limit of Horocycles, but such a point is some, by definition, is some AT of Y. So I want to keep track of the times, the flow times. And here's a small exercise. This set is a semigroup of R. So if you have a return time like this, then you can add any two return times and you get another return time. It's not so hard. It's a little, you have to be a tiny bit careful about the way you take limits, but it's true. Okay, so this is the thing I want to study. And what I'm going to learn about it in the end is that this set, our analysis of orbital closures will follow in the end from understanding this set of return times, of eventual return times. And this set, I'm claiming that we will prove it is either, it's a closed semigroup. It is either everything, this is the case where the thing is dense, or it's entirely positive. And when it's entirely positive, it'll either contain a array, so at some point it'll just contain everything beyond a certain point, in which case it has dimension 1, or it'll be a countable set, in which case it has dimension 0. I'll state this I'll state some version of this in a little bit. But it's this set we want to study. What are the return times from an X to the orbit of Y? Okay, so and why did I give this weird terminology, this weird notation? There's a reason for it. The reason has to do with the way I want to analyze the set. So let me let's see. Let's make a simplifying assumption. Let's assume. So let's set things up a little bit before. So sigma is, as usual, the z cover of sigma naught. Let tau naught from sigma naught to R mod some circle be a one Lipschitz type map. And tau from sigma to R is its lift. Okay, so this map tau is the and let's call lambda naught the stretch lamination. Naught equals stretch lamination of tau naught, and lambda is its lift. And I'm gonna wave. I can either think of these as living in the surface or living in the tangent bundle of the surface, depending on how I want to draw the picture. Okay, so this is the setup, and I claim that it's the interesting part of studying this set is the case when both X and Y are tangent to this lamination. So assume, let's write it, assume X and Y are tangent to lambda, and assume, we might as well assume this, that tau of X and tau of Y are 0. In other words, the picture looks like this. I have my surface. I told Mahan I would use red colored chalk, and I didn't use any colored chalk. But now it's going to be the time to use it. Okay, so here's my periodic surface sigma, and there's a map to R, which we know is whatever these geodesic lines are. Whatever the geodesic lines are, the map tau maps these lines isometrically to R. Okay, on the nose isometrically. And then and then of course, and tau inverse of 0 is some subset. The fiber over 0 is some subset. Let's just assume it looks nice like this. Doesn't matter that much. So I'm assuming that both x and y are tangent to this lamination over the point 0. Okay, this is just to make things concrete. Okay, and then I want to study this set YZX. And I want to study it in the following way. So now I need it's not obvious where this picture comes from, but maybe by the end of the talk I'll have convinced you that this picture is worth thinking about. I guess I have 5 minutes left, right? That's okay. Let me try to say this quickly. So here's a thing to think about. I want L to be a geodesic, which is backward asymptotic to y, to AY, and forward asymptotic to AX. So there are many choices, but let's draw one. So here's one. So in backward time, it's asymptotic to y. At some point, it leaves y and it runs around in some way, right? I don't know. All right, one more time. And then eventually asymptotic to x in the forward direction. So that's L. Yeah, okay, I have to do this one thing I have to do. I have to, I claim that the geometry of what L does tells me a lot about return times from x to y. And it's for the following reason. Let's see if I can, let's draw this picture a little more abstractly. So here's the orbit of x. I think, no, sorry, of y. And somewhere over here is the orbit of x. And then here is this guy, which is eventually asymptotic. I think I just want to say the following thing. So first of all, you see this picture, this is the reason for the notation, right? You see the Z in the picture, right? This is how we remember which side is which of this. Okay, so in this picture, here's the thing to see. So y, because of the asymptoticity in this direction, I can apply a horocycle to y, an unstable horocycle, because it's a horocycle that's shrinking in the backward direction. So this is we'll call this uy. It's an unstable horocycle. And then anywhere I can draw from y. And from x, I can draw a stable horocycle, nx, until it reaches this red line. And I can, again, I mean, I could have done it for any point on this thing. I could draw it like that. They're eventually very, very short, but the one at x is probably extremely long. So let me kind of indicate that it's probably extremely long. Yeah, I'm running out of time to actually explain. But the idea now is, suppose there's a sequence of pictures like this, a sequence of pictures where this part, where the size of u is getting very small. So imagine a sequence of pictures. For example, maybe the next picture, I'll just have translated the red arc by the z action, so it looks sort of like this. And then it comes up like that, maybe. So that it's very, very close to y. Take a sequence like this where it's very, very close to y, and then ask where does the horocycle from x land on this guy. There's some kind of number here, right? So I can just, it's this number in the first picture, right? There's the flow difference along L between uy and nx is some number. Let's call it s for a second. The limit of s, if it exists, is in this set, right? You can sort of see it, right? So if s is converging to some number, then this whole thing collapses down onto the orbit of y, and this s forward image of y becomes a limit point of these horocycle arcs from x. Okay, that picture kind of allows you to do a lot of things. The last thing I want to say Yeah, I think I have almost no time. So let me say the following. There's another way to figure out what this number is going to be, and it's the following. S, I'm going to say S is the slack of L, which is to say it is the limit over large, sort of, let's say maybe A, B, take subsets of L where A from A here and B there, where A is super far in the back and B is super far in the future, of the difference between the time difference from A to B and the tau difference from A to B. So this thing is not in the stretch locus, it's just some geodesic. So it's not, with respect to the map tau, it's not efficient. It's not in isometry. Tau is not in isometry, but it's eventually in isometry. When you look here, it's getting closer and closer to this line where tau is in isometry. So after a while, the difference between the amount of time you flow and the amount of tau you get is getting very, very small. And the total inefficiency of this red path is what I'm calling the slack, is the limit of the t length of this interval, that's what really this is, minus the tau length of the interval. So that converges to something. And that's why, and that number is this, exactly this difference. Okay, I think I am out of time. So let me just say that in the case, so here's a sort of sample result, in the case where lambda is a union of multi-curves, okay, the set of such L's. So now these lines for X and Y are just periodic lines. They're just periodic lines, and I can pick X on one of them and Y on the other in the fiber of 0. The list of such L's is a countable set. And here's kind of where the work is. There's kind of an observation one has to make. The slack images, so the set slack of L, where L is in this set, which I didn't give a name for. Let me call it AYX, is already closed. Okay, so these numbers, I'm going to claim, you have to prove a bunch of things. I'm going to claim that the set of these numbers they all live in this set of return times of the Horocycle flow to Y, and the set of all return times is just a closure of those things. But the theorem is, in the case where lambda is just a union of multi-curves, this set is already closed, so it's a closed countable set. And that gives you one of the cases of the theorem. Okay, so in the case where it's just a multi-curve, you get this closed subset of the real line, which is exactly the set of return times, and everything else follows from that. In all other cases, more complicated chain recurrent laminations, what happens is that the set of slacks is not closed, but the closure contains an interval. It contains a ray, and so you get the other case. All right, I've taken more of your time, so I'll stop.
Has any questions?
Oh, sorry.
Is there a way to see that S is the slack?
Is the slack, like you flow the whole picture down under Horocycle, or yeah, why should I believe this?
So you look at so start here and take this. Well, you're trying to understand this number, but suppose you flow this Horocycle forward a lot until it's way down here. Okay, way out here, tau and t are nearly the same, and you can also push this backwards, and tau and t are nearly the same. Well, between here and there, the amount of time it takes you to get from here all the way to there is the slack of this interval, right? You start here and you go very, very far in that direction. How long is the interval? By definition, the interval length minus the tau difference is the slack of the closed interval from here to some very far away point. But on the other hand, from this point, by definition, from this point, the rest of the distance is exactly the same as what x did. So this is t, and this is t, and t plus this piece is exactly the time for this point. So the difference is the slack. Yeah. And yeah, because things kind of line up very, very nicely asymptotically, this just becomes a property of the line L. Yeah.
Any other question?
Yeah.
So these two cases, the multi-curve case is the Hausdorff mentioned one case.
Yes.
Right. And the general case is where you get a ray is the Hausdorff mentioned two case.
Two case. That's right. That's right.
Yeah. And you had this reference to a theorem of Daskalopoulos and Uhlenbeck. Is that dimension specific, or is that?
No, that works in every dimension. So, right. So the existence of these is a good point. The existence, you can ask what else can you do? So in higher dimensions, if you took a Z-cover of a compact hyperbolic N manifold where N is bigger than 2, you still get this tight map with a geodesic lamination stretch locus by the work of either of the authors that I gave. And so actually in that case, if that is a sorry, this part of the proof works in that case too. So if lambda in say a 3 manifold case is a union of multi-curves, then this countability fact follows. That works. It's harder to understand what happens for general lambda, and the reason is that to be a lamination as opposed to a general current is not much of a restriction in dimension 3 and above. So we just don't know much about which laminations can occur. I think it's a good. In fact, the only example we know in the case of a 3 manifold is due to Cameron Rudd, and it's an example where lambda is a union of multi-curves, and we just don't understand what else happens. So I think this is a kind of good set of questions. What happens in higher dimension?
Thanks.
Yeah.
Any other question? Let's thank Yair again.